All right, let's lock the hell in. All right, I got Discord up. I got the paper up. Okay, wait, so I'm live, right? All right, so I need to be on GitHub. Okay, so I need to sign in on GitHub. Okay, give me a sec here. Okay, all right, all right. So what the frick is that? We want uh, open cap processing or open cap. Um, Actually, should we just reach out to these people? I'll email them maybe. I actually generally I prefer to reach out to people in a public way because um um okay all right, so hold on, I gotta log in to open cap. So I gotta get the password up. Okay. All right. All right, so what do we have to do? We have to. I'm so glad that my quiz is over and I have a full day to just work on this, bro, because where's my freaking rag? Did my rag get stolen? I think it did. Hold on. I'll be right back. I gotta take a rag from here. Alright. Dope. Alright. So wait, let me actually just do this. So chord. Okay, so we want to do this. documents, date modify. All right. Okay, so we're good, and I'm back. So, all right. So what we want to do is we want to post a so what was it? Was it Golf 3? Yeah, Golf 3. Load. Okay. Maybe we should load this. Okay, so um all right, so what I'm gonna do is I'm just gonna get a screen grab of this, I think. Let's turn off my live cam. Wait, what? Oh, live cam's not even in here. Okay, turn off this. I'm just gonna do start recording and then play. Oh wait, we have to do. Okay, wait, so let me stop recording. It's Club Golf Swing. Okay, so just get this. Okay, now open cap core. Okay, advice on. So wait, first we need to go to troubleshooting and read this. All of this stuff Hoist seems to have done pretty well, actually. Um, if you like look at, it's less than 60 degrees, 5 meters. Let's see, what about lighting? Make sure you have black to black corners. That could be it. Best practices. Do not move cameras once you've passed the calibration step. I mean, yeah, I mean, he looks like he has really done all of this. For a 2-camera setup, camera's 30 to 45 degrees off the... All right. Okay, so I filmed that video so I can upload it. Now I can turn back my camera. Okay. All right. Advice on capture issues on capture issues for a golf swing. Hello and thank you for the project. We are a team group from De Anza College. Was doing our final or different equations final project on modeling a golf swing. Our project was to attempt to extract angular shoulder velocity to feed into a double pendulum separate. We are having some issues getting good physically accurate captures. We have tried a number of times, but all right, so now I want to upload a file. I think I can just click and drag actually. So videos, I think it's this, right? Or did I think it's this. MKV, bruh. Golf cap. It's because it's in runtime broker. What is that? Okay, I don't know what that was. All right. Now we need to get terminal open. Okay. fmpeg -i golf.mp4. Okay, re-encode it. Preview. We cannot seem to explain why his body is tilted so significantly, nor why his arm goes behind body. And we have looked into the best practices and troubleshooting guides. I am wondering if it is due to the occlusion of the hands caused by the club. All right. They still work on it, so that's good. Okay, so all right. All right, so we just reached out to them. Let's see, what else do we need to do? Okay, so I need to simulate. Okay, so the main things that I need to do are we are going to fix the ball model. So I'm going to add, because this should be pretty easy. So add uh, wind or drag to ball model. Okay. Code to extract, code to estimate from estimate shoulder torque. So tau shoulder from um, okay, so code to estimate tau shoulder from poise cap. Then simulate so we need to do a bunch of simulate and plot. So I'll start with simulate. Um, um, we need to simulate what? We need to simulate. Great. Okay. So the next step is going to be simulate. We're going to simulate Hoi. We're going to simulate with all 14 clubs. Let me just draw all of the plots that I want to make. So I want to make a double pendulum plot that's like so this is plot 1. Okay. And then in the methodology we explain that we take when theta 1 equals theta 2 as our Okay, what is next? Also, by the way, why is my mic so low? Testing, 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 testing. I think it's just low. Let me boost this. Advanced audio properties. Let's just do 13. Test, test. All right, that seems better. Okay. The second plot is going to be like a bunch of arcs. Okay, then we need a table of distances and club head velocity. Predicted. Hoi. Okay, okay. All right. All right, so we're going to skip that. All right. What's next? Then we need the 3 players. So actually, you know what's so funny? We'll merge this into one table. And then we'll say how good of a player is our player. That's actually really good. Okay, but where's the citations for this? Golf month? They didn't even do the citations. Okay, so we need to I'm just gonna fix these. I'm just gonna fix these. So someone needs to provide a citation, but I'm just gonna fix this. Because this guy's an idiot. Really didn't do anything, but that's fine. Okay, so this table is down here. Is it out here? Tables. Club table, double pendulum table, golfer table. Okay, so we are just going to do, this is going to be arm length. Should we leave it as arm length? Ball velocity. D carry. What is draw? What is draw? Why is this guy not freaking online, dude? Such a... Okay, so I think that this table is not bad necessarily, but since height doesn't go into the model, I'm gonna just get rid of height. So Oh, wait, what is carry distance? Yes. Oh, carry distance is what we want. Actually, so, okay, so wait, first, okay, I didn't even know that, bro. That's how bad I am at golf. So, this is gonna take fucking forever. All right, I'll leave drawl in, but I'm gonna delete height. Okay. So is he actually editing anything or no? I feel like he's just fucking jerking off or something stupid. All right, let's Okay. Um. All right, let's just try this. So I'm gonna comment this out. I'm gonna say columns 8. Okay. I'm just gonna put this as tau shoulder. Is that how I call it? What is the symbol that I use in my parameters? Tau shoulder. I use the whole word. So we have to use the whole word. D carry. Oh, D roll. Bro, I'm so dumb, dude. Lol, dude. I can't believe I just did. I googled that shit, dude. I didn't even notice that it was roll. Silly as hell. Okay, max club heads. So something got. Oh, yeah, because we have to delete height. Height is getting deleted. All right. That looks a lot better. And then we can just look at. We can just do this club head. And we'll just do this. V club. And then we can just do. I think we should just be able to do L1, right? I don't really like that. I feel like arm length makes sense. Arm length, V club head, tau shoulder, V ball. Okay, I removed height from that, so that's a lot better because we are going to use this to compare with our model in validation. So we're going to simulate these different arm lengths with these torques. Wow, so wait, does it really roll for this much? We gotta get check. Let me do this. Okay, so that's that. I guess I'll find the fucking citations for this, but like, uh, okay, wait, hold on, let's read this. Carry airborne distance. Ooh, we could just do that. We could just say that instead of time to first because I kind of hate how I said it. Airborne, what did they call it? How is the bro? This D-roll thing seems so wrong. Oh shit. I mean, who honestly is thinking that that is how far it's rolling? I don't believe that. Okay. Including airborne, airborne, carry, distance, and club head speed. Okay. So there's that. Um. I'm complaining about them using ChatGPT to ChatGPT. Now that's good stuff. I mean, I think I'm just gonna drop the uh so wait, what did it say the average was though? Or wait. Yeah, it's saying that an average player drives 300 meters. Wait, wait, actually, is that true? 300 meters in yards. Isn't a yard? Yeah. That's just so not true. Like, the ball does not roll 130 meters, bro. That's so stupid. Bro, I just want to ban this kid. This kid's bothering the fuck out of me. Alright. So we got the video, so I can just close this. We do need to talk about there's a whole bunch of to-do list things that I'm just like not doing. So you have like 6 hours. I need to do chem at some point, but like, you know what I want though? I do kind of want some LaCroix. Might get a LaCroix. Wait, why don't we just call it carry? This is stupid. Let's just call it carry. This is dumb. Carry. Ooh, let's just do carry and total distance. So, um, yeah. So we're just gonna delete this column, make it 7, and then just delete this garbage, this garbage, this garbage. Carry. So see how this is fucking all. So we do want to change this to club head velocity. What if I change it back? I do want to transpose this really bad. So what would that look like? That would look like or average, pro, unrealistic, elite, and then stat. Okay, so all right, so wait, hold on. Okay, wait, hold on. I'm just gonna say provide the following stats for 3 tiers of golf players of skill for golf players. We want the arm length. We want Yes, their club head velocity. We want their shoulder torque. We want ideally the wrist torque too. And then we're gonna have a comment about that Hoy comment. No wrist torque. No wrist. All right. So wrist torque. Wait, why is ball velocity? What's the difference between club head velocity and ball velocity? Oh, I get. Okay, actually, you know what? That's good. We want ball velocity. Ball velocity. Um, carry distance. Total distance. For a drive. Okay. With citations. And you know what? I'm gonna freaking kick off a deep research, baby. And I'm gonna get my LaCroix. To provide accurate stats, can you please clarify? I honestly am not sure. Male golfers. And yeah, amateur, intermediate. I don't know what for the tiers. It be used to compare to my double pendulum simulation results. Okay. So whatever classification used, we just need good cited data. No golfers. Make it easier. All right, so we'll wait for this to finish. In the meantime, we can do some stuff. And then I am going to actually just write this table because this guy, I mean, is just a fraud. Collected data of golf clubs. You didn't even do that. You didn't even do that. You didn't even do this. You didn't. I'm just gonna delete this. I'm just gonna do this, bro. Cause you just didn't even do that. I did that. All right. Presentation's good. You did the presentation, but you didn't do it. You didn't make this. I made this table, and I cited it. All right. I don't give a fuck. I'm gonna go get a LaCroix. not gonna rage too much because it's not worth it, bro. But all right, let's all right. So we'll fix this table and we'll format it nicely. Dude, I wish I could just hide it though, because it bothers me that it keeps flashing up and down. All right. Okay, so this data we can delete, right? Okay, so let's do a ball model. I'm excited. I wanted to do this for a long time. So in here, no, in here, we have a ball model. And, oh, so, okay, wait, hold on. I forgot to say, we need to talk about, in the paper, momentum transfer. Okay, so, I can just write this section right now. So, okay, so momentum transfer. So, all right, so we'll do the double pendulum Lagrange, get the equations of motion for that. All right, momentum transfer. So I'm gonna do a double subheading for that just to like get it. Can I go over here? Okay, so so the transition from the swing model to the ball model required the transfer of momentum to the ball is governed by, what is it called? Is it elastic or inelastic? Elastic collision. Is this like elastic collision? This is with no momentum loss, right? Yes. Okay. Is governed by the transfer of momentum to the ball from the club to the ball in our model is governed by elastic collision. The mass, the final velocity, or the velocity of the ball can be calculated by solving the system of equations that relates the conservation of momentum and conservation of kinetic energy. Okay, let's add the equations. So basically it's that, so we have, what is U1 here? U1 is the velocity. Okay, so I actually am probably just going to rewrite the model because you can close this. Okay, so okay, so if if V1, so wait, let me just remember. So the club is going at V. Um, so the thing about this that's like so crazy is these are basically the same section, right? Okay, first off, totally unsighted. It's like, why would you put this in if you don't know that's true? It's crazy. It's fake news, bro. Okay, so this is all garbage. I am probably just going to delete all of this. Factors affecting the swing, what a normal shot looks like. I mean, all right, so I'm probably just gonna delete from here to here. I am probably gonna delete all of this because this is just nonsense. It's not related to our model. That's the problem with Rashad, bro. Rashad is a great guy, but he's also trying to pull a fast one over me. And I'm telling you, you can't pull a fast one over me because I'm too neurotic. I can't have a fast one pulled over me like that. All right. So in the background, we basically motivate all of the models. I think that that's fine. All right. So, what this means is I need a refresher on some actual basic physics. So, so we have, let's say we have a mass. So we have M1, V1. Well, actually, I need to be careful because no, if we have a point mass's velocity, then that is what it is. So this is actually going to be M2 from the model, and then the club is going to be, all right, so, because I kind of want like a global namespace, if that makes sense. All right, and this is moving, and then this thing is M ball V2. And actually, this is going to be V2 as well. Okay, so let's just do this. If M1 and V1 are the mass and velocity of the club head, respectively, and M2 and V2 are the mass and velocity of the club head, or of the ball, we can then we can obtain the following system of equations. So here we are going to have the kinetic energy. So the sum of 1/2 mi sum 1/2 mi vi squared is equal to, and how did we do this whole thing? Huh. And so that's conservation of kinetic energy. Now conservation, so this is Um, we get 1/2 m1 v1 squared plus we assume the ball has 0 velocity before impact. So this is going to be plus 1/2 m2 v2 squared. And then we can just do cancel. Is equal to 1/2 m1 times v1 prime. How do I do a prime? Squared. v1 prime squared. I wonder if I can just do a space here. I need to think about this. How should I format this? This kind of doesn't look right. Maybe I should do this. V prime 1. That's not bad. We assume that as and v prime 1 and v prime 2 are the velocities after collision. Okay. So how did I solve this thing? We solve for we solve for v1 and then we plug it in, or what? How does this work? Oh, look at that citation, bro. Oh my god. Okay, so that is sweet, man. Do you see how it did it? This is how you make a table, bro. Okay, so we need to collect all the sources. We provide a range. All right, so we need to make this table. All right, so I'll do that table. So we got the golfer table. Where is this from? Taiwan? Nice. Fuck yes, dude. Okay, so we have to make this table. Okay, so I'm gonna fix that table. All right, but first we need to do some physics. All right, so I'm gonna duplicate this, do a new thing. All right, here's what I need to know. Help me. So okay, if M1, V1 are okay, let me just do it on paper. So if we have The thing that's funny though is this is much more of a homework thing than like a um should I just get rid of the single pendulum? This kind of sounds like shit, but um we need the broad strokes thing. So 1/2 MV1 is equal to M1 V1 prime plus M2 V2 prime. Okay. Then we the 1/2 gets rid of. Now we have momentum conservation. So the amount of momentum of our thing is that. So then we also have M1 V1 Okay, so this is a number and this is a number. So if we change this around, we get M1 V1 prime is equal to M1 V1 minus M2 V2. This is not squared. M2 V2 prime. Okay. Then we divide by M1 and we get V1 prime is equal to V1 minus M2 over M1 V2 prime. Okay, then we substitute that in. So then we get M1 V1 squared is equal to M1 times V1 minus M2 over M1 V2 prime squared plus M2 V2 prime squared. Okay, and so this will allow us to solve for V2 prime. Okay, so let me just make sure that I got this right. All right. If M1 and V1, M1 V1 are the mass of a, okay, we have two blocks sliding on frictionless surface. M1 is moving at V1 to M2, which is at rest. Am I right that to solve for the after the velocities after collision, I do the following. Form a system of equations for conservation of momentum and kinetic energy. Okay? So basically simplified, it's M1 V1 is equal to M1 V1 prime plus M2 V2 prime. And then M1 V1 squared is equal to M1 V1 prime squared plus M2 and v1 prime and v2 prime are v after collision. m2 v2 prime squared. Then I can just solve, and I think there's like a negative solution, so we take the real solution, right? I solve and take the solution that is non-zero, or that is, take the solution where v1 not equal to v1 prime. Okay, great. So, let's go here. I kind of don't love how it's formatted, but we can just do this. All right. I mean, who cares? Plus 1/2 m2 v prime 2 squared. Okay, great. And we also have the equation m1 v1 plus cancel m2 v2 is equal to m1 v prime 1 plus m2 v prime 2. All right. So this, so wait, but I kind of want to form the quadratic. Is that crazy of me? So let's just do some, let's just do some shit. Okay, so eq1 is equal to, we get 1/2 m1 times m1 v1 plus m1/2 m2 v2 is equal to 1/2 m1 v prime 1 wait, we screwed this up. This needs to be squared, and this needs to be squared, and then this needs to be squared plus 1/2. So obviously I can get rid of the 1/2, but I just wanted to write the whole thing out because sometimes you make like little things and then it becomes wrong just by accident. So I don't want to get anything wrong at all. m2 v prime Okay, now E2 is equal to M1 V1 plus M2 V2 is equal to M2 M1 V1 VP1 plus M2 VP2. Okay, great. So now we have eq is equal to eq1 eq2. And I think what I want to do is I want to solve eq for VP1. Can I do that? Can I just do that? Right. Oh, you know what? Isn't there like a solve for? Hmm. Oh wait, they just have it here. Oh yeah, why didn't I do that? I'm dumb. Oh, I did. No, I did. Um, I'll just say the solution, the result is the solution set will include a trivial solution where v1 is equal to v prime 1. The other solution provides us the true final velocities. Okay, great. We then use the club specific loft angle and the magnitude of the v prime 2 as the initial condition of the trajectory. I'm wondering where to put my block diagram. I'm not quite sure, honestly. Um, we need to add so in model validation, some factors we are ignoring. What kind of header is that? Okay, limitations. Drag. Why do we have two? This is like repeated bullshit. Right, so I just want to. I kind of want to just write it all myself, bro. What's happening? Okay, so let's just go back to. So I want to do. Okay, background. Okay, so I think I'm going to take my block diagram figure and now put it right at the start of background. So, and I want it below that section. So I'm guessing that. Ooh, I kind of don't like that. That's like that. Okay. Can we just? I don't want to do a page break because page breaks are really sus. Can we do top? Oh no. Okay. This work. How am I gonna do this? The our work provides and then do I have a tag for it? A pipeline to take film of a golf swing and use it to drive a carry distance prediction model. At block diagram demonstrates a block diagram view of the components of our work. Okay, great. Now we can jump into swing model. Momentum. Okay, great. So we still need a double pendulum and equation of motion, but we do momentum transfer. Okay, so now it's time to move on. Okay, what is next? The next thing to do is the ball trajectory model. We get to model now. We actually finally get to write some code. All right. What's happening here? So I forget. So we need to take club head velocity. So maybe I'll just write a function. That does this. So great. Okay, so what we're gonna do is it's just gonna be compute. Okay, so function compute elastic collision. All right, so we get M1, V1, M2, V2. That should be all you need, right? And then we just return V1 val, V2 val, end. All right, so we should be able to put this in here, and then all we have to do we use anything else in here? I don't really know. We use the val. All right, so in that case, we can just write V1. All right, and then V2 was, yeah, okay, great. Now we can put this, oh shoot. This is going to be V1. let's make this v1 prime. And let's call this v1 p. I don't know. And then v2 val is, but yes, and v2 prime is the ball velocity. Great. So I can move this to golf model. And then let's just export it, I guess. Compute elastic collision. All right. And then v2. So that's the problem, right? Is that this whole thing assumes that v2 is 0. I don't want that. Is that real? Whoa. This is why you gotta learn mechanics really well, but I'm not doing this right now. All right, let's just, warning, this assumes that v2 is 0. All right, let's just delete this. Okay, so I should be able to do this, right? It'll error because it doesn't know what those are. But, U1, where's U1? Where V1 Nice. Okay, good. So we're good on that. We are good on that. We are good on that. All right. Now, um, okay. So now, okay. Where can I learn about the dynamics of a real golf ball flight? This model is just a bit too simple for what I want. Open foam, bro. This fucking guy, dude. I'm not running open foam simulations, dude. That's ridiculous. Dude, the golf people are crazy, man. Let's see. Can we get this DOI? Where is the DOI? Oh, wait. We have it right here. Is this the whole thing? Okay, wait. Actually, you know what I want to do? Um, I'm trying to think. What the hell? How is this off? Oh, you know what? I know why. Alright, now it's bright and early in here. Holy cow. Okay, nobody is working. That's fine. Actually, he might be working on the presentation. Where's St. Andrews, bro? It's so cool, bro. Nah, see, that's fucking cool. See, that's the thing about doing the actual research is you just learn all this really fun stuff. Oh, that is so interesting. Okay. Um. Okay. Uh. So I want. Where can I learn? Can you just help me and summarize? What is the research? No, you idiot. No, I mean like, okay, just explain the model. Just pick a model to describe. Uh, like, what is this? Coefficient of drag? Oh, dependent on the. Okay, great. Wait, what is this? What is semi-empirical 2D OD? What does that even mean? A plot where we vary the plot vary the golf ball mass. Maybe? I don't know. All right, let's just do this, right? So we're gonna. What is the 2m? Wait, is it? Oh no, it is no, it is a second OD. Yeah. What the fuck, dude? I swear sometimes you just get GPT into some weird zones. It's so funny, bro. Wow, but they actually I mean, I don't know how much this actually matters, but well maybe okay, so we'll make a parameter and we'll pick so low speed regime. Oh, so that's kind of interesting. Actually, is this model even right? Yeah, we need to go into this. Really? Yeah, I'm pretty sure that this model is wrong, actually. Um, well, oh no, you know what we can do, actually? We could just, so we could just make it a second order equation. That's actually probably the right thing to do. Or is it the same as if we just did d2y? I don't remember if that's right or not. Okay. I think that makes sense. So it's going to be a 4 ODE. Okay, wait. So what are the eeks of motion for just gravity, and we have an initial velocity vector? Yeah, let's just do that. Okay, so I'm going to start over. Do we want to do this? We could do, yeah, vx0. Yeah. No, that's not what we want. Okay, nice. So this is our model. Now, the only thing that you change is we let an observable be given by square root, not of the initial, right? Is there an add observables? Or wrong one. Modeling language. Where's the language? There we go. Okay, I don't think so. So we can just do. So I don't know. Can you do this? This is probably gonna say we don't know what this is, but I think you can just say v of t. I think you can just be like, okay, we got this thing. Let's see. Does this work? Okay, so what do we want? Let's just do I think it's called mtk compile now. Oh shit. Wait. Oh yeah, because we need to update this. I think let me go look and see. Yeah, so we should probably delete this because this is outdated. But if we go to here, we have all these updates, right? Okay, I think so. Yeah, I think so. So we just need something like this. Stop effect is the greatest. I use stop effect everywhere. Unforced single pendulum, let's go to trajectory. Just do this. Okay, great. So I think that this works, right? Okay, wait, hold on. Oh, it's invalid units, that's fine. Yeah, let's see, here we go. It's probably um if it's an observable, it should be totally determined. G meters per second squared. Oh, this because ball mass. Ball mass isn't even used. Radians isn't used. Where's the error? But it doesn't say in equation 1. Meter per second squared. Can I just... Okay, let's just try this. Okay, so that works. So now, and I think this needs to be at mtk compile. I think that's the real way to do it. So here's what I... So wait, why isn't it what the... Okay, hold on. If I just like, can I stick this out here? Does this work? Oh, good. Okay, so if I just took this expression, what would the unit of this? Does this work? Get unit? Or does it like fail? Meters per second. So then I don't understand. Like, that's what I'm saying. Okay, so you know what? Let's just not use it then. All right, so the idea is that we're just going to go here. Right. Okay, so we're not going to do this whole thing. We're just going to use... Oh, because they want to parameterize it. Okay, so... on the mass... Okay. Mm. Okay, we're almost done with a ball model, which is good because I actually do want to get some results and compare. So let's get back to the dynamics. So it's gonna be K. So this is gonna be actually the change. The acceleration on the ball is gonna be minus K times. I wonder if I can just do like how do I just because here's what I'm wondering. If I do this, does this just fail? It says because V is not an unknown. But then if I do this, how can I say structural parameters, defaults, equations, constraints? I don't think it's constraints. Because what if we did? Okay, wait. Let me just. Oh, actually, did this work? Oh. Okay, wait. Hold on. How do I do this again? Do I need a comma still? Okay, awesome. So let's just pick that the initial velocity is like 100 meters per second and 100 meters per second. Okay. should be the simplest model ever, right? What is... Okay, wait, actually... Oops. Wait, what? Why didn't it go up? Right. Because... Oh, because I didn't do any initial conditions. Wait. These equations are wrong. Can I do this? So hold on, let me look at it. Because what we're specifying is Vx. We're specifying the initial. So I wonder if I can put in Vx0 and Vx0. Can I do this? That's... Oh, wait. Vy0. Holy. Holy moly. All right. Okay, so this is the stupidest graph ever. I'm trying to plot the pair. So if I do sol ball of x and y. Oh, you need a... Okay, and then I wonder if I plot this. How do you plot... So let me just ask, because I always forget. How do I plot lists of XY coordinates? Julia. Let's just do this. Does it end with terminated? Not terminated. Okay, so this is dumb. Okay, so if you hit... What is... That seems about right. It should have this stop effect on it, right? What the hell? Why didn't it stop? Oh, wait, no, why didn't it stop? Wait, is this X? Oh. This is because the time steps are really okay. So let's just do 100. Let's do something really long. It doesn't matter because it should terminate. Okay, good. Finally. Yes, what a good model, guys. Okay, great. But this is psycho because why? It does terminate, but then after about 20 seconds. Wait, what? How did it? Why was it saying 2000? Okay, no, it's good now. Okay, so the ball model is redone. Wait, let me ignore the backups. Okay, so we still have a lot to do. Okay, so we have this trajectory model. Now we're going to add basic drag. Okay, and I'm going to have to build the model tables for all of this and everything. Great, awesome. Okay, so the next, re-implemented trajectory model be a bit nicer. So I'm actually going to, I think all this stuff. Okay, so let's just, so we don't even need this. We had this, but I'm just going to delete this and this. Okay, great. Okay, great. Okay, what's next? We need to add drag. I want to change this to be, oh, the problem with this, loft angle. Okay, yeah. So the thing about loft angle is that it's not even being used because we just specify the components individually. All right, so we have this interface thing that I need to figure out. Is like, we have, okay, so I think what I should work on now is get a simulation from the club. We get the club head velocity, and then we make a function that basically simulates I know we could do some composition thing, but I'm gonna do it outside of MTK to avoid having to write to read documentation. But I think it'll be fine because we're basically going to have a function. We're basically going to have a function that takes in parameter values for the ball and parameter values for the swing, and then simulates one, and then it calculates the velocity, and then it simulates the next one. And that's pretty much it. Okay, sounds good. I mean, one question is like, how valid is the assumption that that drag really is proportional to? But that gets into like, all right, now you're solving PDEs and you're like figuring out all this crap, but like, it's too much. So the acceleration in the x direction is going to be minus k some parameter times the magnitude of the velocity times the magnitude times the so like, why is this the drag term? Oh, it doesn't even let me select it. Why is minus k v vx the x drag term? So like, what is it about that? All right, dope. So this is going to be minus k times v times vx. And this is going to be like this. Oh, yeah. Holy cow. Okay, so let's just say, so we, instead of doing this, we are going to do then this is going to be loft. This is going to be, so wait, hold on. In the x direction, so we have this triangle. This is the theta for the loft. And the Vx is going to be cos. So it's going to be V cos loft. All right, so it's going to be V0 times cos loft. And then here we're going to get V0 times cos times sine loft. All right, so now if we do this, I want to change this to point to over 8. That seems a little high. So now we've sort of swung the other way, maybe? Okay, for like a... So do we have that? Is that in here? Oh, but you know what? Right. It's because the club... Because I'm thinking of club head velocities as my barometer? My barometer. But that is not accurate. Because... Golf.com, baby. Ball speed. Okay, ball speed. Let's do 76. And what about the angle? What's a typical angle? Typical angle, launch angle is 14. So we're going to do deg to rad 14. Then we are going to make this 76. All right. Wait, but was that was in meters per second, right? All right. That's the ball speed. So let's see, how far do we expect that dang thing to go? Carry 256. No, see, that's not right. Something's wrong. 60 meters? What if I make this 150? If I double this, what happens? But also, does this angle look wrong? Oh, but you know what? Actually, can we make this like deg to rad 30? See how far it goes, because it's gonna go way farther without Magnus. Magnus lift is actually a super big a deal. All right. Okay, so it seems like my model is greatly. Yeah, I'm just gonna talk to it. Yeah, so it seems like my model that just includes gravity and drag greatly, if I use the launch angle as the initial vector for 76 meters per second of ball initial ball velocity, the magnitude of the velocity, it predicts that it goes like 80 meters, and my suspicion is that this is likely due to the spin on the ball, or rather the lack of accounting for the spin on the ball, because if I increase the launch angle to 30, then we start to see more realistic numbers, like close to 200 meters. Hmm. Okay, well, it couldn't hurt. So KL, I mean, let's just see. KL is equal to what? 0.1e minus 3 lift coefficient. It's in meter. Okay. So now we're going to put in this equation here. Why is it based on the other one? Why is it based on the other one? So you know what? I'm actually curious for a representative thing. Let's set K. Oops. Let's set this to 0. And let's see how far it goes. Did I do 30 degrees? Yeah, so that's psycho. But if we do 14, which is kind of close to what it was. Still psychotic. Okay. So, uh, so the carrier distance prediction is total freaking bunk. V0 is 150 meters a second, though. Is that right? No, but that's not what it's supposed to be. It's supposed to be 76. But even still, should be linear, right? Okay. Oh, that's actually perfect. Dude, somehow just a basic that's what's crazy, bro. Somehow just a basic model is the best. This is like almost dead on. Because what did it predict? Alright, so we have Sol X the end. Hello? What the hell? I swear, sometimes this thing is crazy. Alright, so somehow okay, so we're getting close to simulating both models at once. Oh, that's so fucking cool, bro. Oh my god. All right. So, all right, so what we want to do for validation is we want to take golfer data and we need to split it up and combined. So, swing model, test the ball speed from torque. So I want to rearrange these actually. I want club head speed to be below these two things. Okay, so we need to find all of these sources and get their bib texts. I feel like it's just making this up, bro. Is the fucking Reddit thing in here? I wonder if I just I wonder what you're supposed to do about that. Is it this guy?
So
Where was the video that I found?
my personal longest recorded drive in competition is 480 yards. The Guinness World Record is 515. To be totally honest, I'm thinking more about 600.
All right, here we go. World record is in play. Kyle Berkshire is going to go for it.
Go on. It's going to roll out 340.
A lot of crazy stuff gonna happen. I mean,
There's going to be a hole down there. The ball can always roll into it. There's going to be green. It could get a little off the green. There's going to be a little bit of room behind the green for it to really stretch out.
If I watch this, it can't get any better. Now it's just a matter of ball speed.
Yeah, and that's where we'll see that 600 plus yard drive.
Wow. If I could just total with this, I'll get 535.
Yeah, we don't need to hit anymore. We're good.
If you pan over and you show the flags, it's about, at the moment, 20 to 25 miles an hour. Tomorrow, we're expecting 30 to 35 with gusts over 40.
Oh, come on. Take the...
So I think we're going to hit something pretty incredible tomorrow.
Okay, so I think maybe we have the speed, have the distance, but it gets caught up in this brush.
Look at his feet, dude.
Balls.
Balls.
Maybe we have this.
He's on his tippy toes on the left arm straight though. Holy shit, dude. That's so crazy. You can't even see it. That is actually insane. That's crazy, dude. What the hell? Okay, so what was I talking about? I got distracted. Okay, so maybe we should not. Oh, wait, hold on. Oh, no, K is 0, so that's fine. All right, so what I think we should do is build the ball. I don't even need this. This is all good. This is garbage. Because we're not doing any bounce. We're just predicting carry distance. What time is it? How much time do we have? 6:30 already? Holy shit. All right. So, okay, so what I want to do is, in our thing here, okay, so a ball trajectory model was created to predict the airborne distance of the ball given the given the initial velocity magnitude as a result of elastic collision. The specific club used determines the horizontal and vertical components of this vector. The ball trajectory model was created to predict the airborne distance of the ball given surprisingly the best model in terms of realistic prediction was a model that neglected. Okay. Two model variants were compared. One in which the only force acting on the ball is gravity, and another in which a drag coefficient, or in which drag slows the acceleration of the ball proportional to slows the velocity. The specific Hey, this is starting to come together, my bro. This is starting to come together. Oh wait, I forgot to do. So this needs to be in. So this is swing model. There's a motion comment that will use computer vision. Okay. All right, so we still have these things to do. All right, so the first model. So so are we gonna do a model table for this? We probably should, right? If we have a model, we should have a model table. So a model table is going to be just or I think it was that, right? It's gonna be the same, but what is it actually? It's so yeah, it's gonna be uh uh it's gonna be x vx y vy, and then I guess we do need to do the equations of motion. I haven't really thought about that for the double pendulum because the double pendulum's equations of motions are unwieldy, but we are going to include them. I don't know. I probably should include them. Okay, so what are the parameters of it? It's G. What else is on it? G, V0, and K. That's it. So, and K is cited. So it's a 3-parameter model, and then we're going to state these equations. Okay, great. So we're going to have V, so we're going to have kind of like 5 states, but I know it's observed, and you know it's observed. Okay, so V, K, and v0. Okay, so that's the model table. So I wonder if we can actually go to this data. Okay. Should just need sys. And now you can pass in, so, okay, so let's just say model sims. Okay, is that it? I think that's it, right? So then we just return this. Independent variable states parameters. And now we can provide, so we can get this, and then we can provide an order that we want. So the order is going to be, so get D. What is get D? Get D is, I think that's it, right? I'm just pretty sure that this doesn't run. All right, so sys equals double. So we can just call model sims of sys. And then we can just pass an order. I don't know, this seems janky, but then we can pass in order equals each index sims, and then we put in order here or something. Does that work? Let's comment this out. So what was this originally? Sim order. Okay, so then this is sim order. Okay, yeah, that's fine. And then we can do sims equals model sims. Because like maybe you want to subset it. I don't know. This is pretty bad code. And then we want sims. We want sim order. I mean, maybe I could just rearrange the rows. I think that's probably better to do it after, actually. So, all right, so we want something that gives the data frame, and then you permute the rows after, and then you do it. So, and this we want to be code symbol. Okay, so we are not going to change the order whatsoever here. So I think we don't need this, right? It really only gets used there. We got this, this. Okay. And what we want is the data frame. Okay. All right, so let's just try it, right? What's the worst that could happen? What? Right. Key VY not found. Because of defaults? Yes. So we need to, but wait, VY not found. When did they do this? This is new. Wow, they started adding some real structure to the tearing state and all that or something. Pre and initial, a whole bunch of types to smart. Okay, so what's happening now? So kind of actually that kind of breaks the code. It's kind of annoying. I think I'm gonna bail on this, and I'm just gonna do the following. We're gonna have model. So let's just do model sims ball or sys ball. So wait, let's close this. Let's do this. Okay, so we want to actually get rid of. Let's get rid of the lift coefficient. Let's call this. What is the most canonical CD? We can leave it as K. Who cares? Let's just make sure that this is right. Drag coefficient of the ball. We have a citation for it, so it's fine. Just delete all this shit. Ugh. Does this work? Okay. Okay, so let me just write out the table by hand, because like, what do we really need this all for? So it's just gonna be. So let me look at what we had before. So in the model table of this, okay, it's gonna be t time s. You know, it's gonna be that. Then it's gonna be x vx y vy v0 lift or loft. Is it called lift or loft? Golf loft. Yes. Okay, so we got loft and then we got K. All right, and then we got the units. How do you do that? Let's see, code types. You can do that. Okay. We've got, so this, it sucks. Bro Bible. I mean, these are bad sources, but Reddit. Okay, I don't know. What were the columns actually? Okay. I think I'm manually just gonna make the table. Okay, so um actually, you know what? I'm not even going to do a model table. What's the point of the model table? The first model has simple dynamics that follow the following equations. So we're gonna have uh 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 I don't even want differential, but I kind of want to include my shit. Do I? This is equal to 0. Dot y is equal to vy dot vy equal to minus g. For x, the horizontal. So you know what we could do? We could just build a simple table that has the okay. So okay. Okay, so fuck it, let's just do this. This is gonna be let model table traj model table equal table. Okay, it's gonna have, I don't know how many rows, but it's gonna have columns. I'm not gonna include any code, so it's just gonna be like 1, 2, 3, 4. Okay. let's get the I'm pretty sure I can just okay, so this is going to be the same exact except for same as this, except we don't need, this is just going to be symbol, name, unit value. Okay. What do we do next? Is the data. Okay, so first I actually want to include this. So we need to make it a figure. So how did we do that before? So we did this. So we did this. And then we want this to be a trajectory model table. And where's our error? This is wrong. Okay, fantastic. Table 2. Okay. This is going to be trajectory model table. Now we can finally do, so we can skip time. So now we just have to do, it's gonna be, how do we do this? We have to put it in content blocks. It's so annoying. This is gonna be T. Is there really a better way to do this? There's gotta be a better way to do this. We can skip time actually. We're just gonna do X horizontal. Oh, this is not. Meters. 0. How does that look in comparison to this? Let's just do this. I don't know what's more correct, honestly. This is going to be V0 cos loft. Let's just call it theta. Okay, so then theta loft angle. This unit is meters per second. Meters per second. Loft angle radians. And theta is Okay, then let's do, this is going to be V0 ball initial ball velocity magnitude. This is going to be in meters per second. And this is going to be simulation dependent. And then finally, what's our last guy here? It's going to be loft. Oh, wait, no, wait. Do we have everything? I think we have everything. That's it. Okay. Oh, G. G, gravitational constant. Meters per second squared. And then do we have a value up here for that? Minus 9.8 or 8, yeah. See, that looks different than that one, doesn't it? He'll never notice. He'll never notice. Ugh, that pains me, but it's okay. Okay, and this is 9.81. Okay. So that's the model table for the trajectory model. Okay. Finally, I can just do this. Using now the drag, the model, the inclusion of a drag term proportional. Oh yeah, did I add k to this thing? No. Drag constant is in meters to the -1. Uh-oh, something. Oh, wait, no, it's okay. So then this is going to be 0.0052 or something like that, right? So then we get minus k v. Oh yeah, actually, we want to add v ball velocity at t. Instantaneous ball velocity. This is going to be also in meters per second, and it's going to be equal to square root of vx squared plus vy squared. So this is going to be kv times vx. and it's going to be minus k v vy. Oh, did I never change this? Holy shit. Wait. No, but this should only dampen it even more. So wait, hold on. What's our setup right now? Actually, that's not that bad. I mean, it's definitely... Wait, did I write that right? What is the equations of motion here? Yeah, of course it is. All right, so then that's interesting. The ball mass doesn't get used anywhere, right? How come this is fucking full screened? Here we go. All right. Good stuff. All right, so now without drag, okay. Can I get a footnote on a... Of course I could get a footnote on a table element. But can I? I don't know. Maybe. Let's see. Okay, so that's good. So for the drag value... Citations. How do we get the bib text, bro? How do I cite it? How do I cite it? How do I cite it? Share and cite. Beep text, beep text, beep text. All right. All right, let's go. Oh, that's sick. But he fucking... Bro! Wikipedia? Oh my god, dude. You can't cite Wikipedia. That's not what that is. Bro, exactly, man. Come on. How is this a fucking citation, dude? Now this is a citation. Ugh, what a jokester, bro. They don't understand, man. You're not allowed to cite Wikipedia. Hey, you know what? I should chill out because I'm about to cite Reddit. So, anyways, that's crazy. Okay. Oh wait, in the footnote we wanted to do. I wish I could just spend like 1,000 hours doing it. Wait. We have a problem. All right, that's chill. Should I cite my gravitational constant? Who the fuck thinks I should? Who the heck thinks I should? Okay, so we're good on that. Now we have this. Um, um, a callback is introduced into. So wait, actually, I need to in here. I need to talk about double potential. Equations of motion. Stopping condition and uh callback basically. All right, so I think it's time to um tell you what up. Um yeah, we need to I need to rewrite the I need to rewrite this because it's not right. It's a total lie. All right, so let's do the double pendulum. Okay, great. Okay. Now we introduce the double pendulum the canonical double pendulum model. The Lagrangian is represented is so we need to write, so this is going to be L double is equal to, this is gonna be doozy. So do we have L? We need to get, so in here, I think I should be able to just do this, right? I don't think it did anything. I wonder if we can just write K. Okay, so we write that um well, actually I need to do cite this what is it called? Prose kind, bro. What the hell is it called? Form prose. We introduced the canonical double pendulum model. The full written Lagrangian and differential equations are meant for reference but not interpretability. Review the code in Jane for the full derivation. The Lagrangian is, so we have K So wait, actually we need to get the right one. So T is the kinetic, right? So T is equal to and actually we're just gonna do code, I think. So let's just do this. So this is gonna be T, V is equal to P. Okay, but what if I do equations of double? It's like oh wait, as the differential equations are long, see the appendix. So where's the appendix? Isn't there a section for like appendix? Um, uh, we do this. All right, so then here we're gonna do the differential equations. And this is going to be K, and then we can is this can I do this? Am I allowed to do this? Yeah, I didn't think so. So I can do this though. Okay, great. So we did both of this. Now, um, um, uh, so I don't know if here is where we want to talk about this, but basically we want to say that. Let me read this. Um, can I put this at the bottom and the compiler will still know? No. I love how these weasels, bro. Eh. It is because of the club brand in a decent form. Ah, thank you. Wise one. Wise one. Yes, yes, yes. It's like, Jesus. These guys are a little crazy, bro. But anyways, we're going to delete all that because it's all wrong. Hui did a good job with these diagrams, though. I like these diagrams. Okay, let me actually read what he wrote, though, because right and left arm rotation. Actually, let's do limitations. And then future work. How many pages are we at? 12 pages, but like most of it's diagrams and crap, so it's not terribly overwritten. I mean, because you don't want to just vomit a bunch of too long nonsense. Okay, we need to get going. So this. Okay. We now discuss the methodology for determining the determining the club head speed at time of collision. We implement a callback in the differential equation integrator that will perform a root finding routine to calculate the exact time when theta 1 is equal to theta 2. We need to discuss this corresponds to the point where the club and arms are aligned. Okay, so limitations. So my stuff is gonna be okay, we need to go through and list all of them, but this one is going to be the I think I'm just gonna say it here. So we need to. Okay, so bro. Okay, give me a minute. I don't want to go get some food. Okay. See, where is he? Okay. So, um, um, Okay. What do I need? I need a citation for this. Bro. What's it called? Asher or something? A. Hmm. Okay, so this is all just mathematical background. We will show now that we'll show later that that's the biggest thing actually. The biggest thing to do is the cap to T tau shoulder. And wait, what? Wait, what? That's a pretty good diagram. Better than my diagram. Okay. Um, where are we at with this one? Oh yeah. But see, The assumption of elastic. See, that's the kind of stuff that I. Okay. Bro, it's crunch time and the boys are fucking. Yeah, bro. All right. Oops. Okay. What is next? Let me just read the whole paper. Why don't we read the whole paper? Can I full screen this thing? All right. Golf swing simulation and carry distance prediction from smartphone motion capture estimates. Double pendulum models of the golf swing are well established in sports science literature, yet most studies focus on theoretical dynamics or expensive motion capture that ignore carry distance prediction. We present an open source pipeline that 1. Uses OpenCAP's video analysis to extract shoulder torque. Ford simulates a subject-specific double pendulum model in the Julia programming language package modeling toolkit. And 3. Augments the swing model with a ball trajectory model to predict carry distance. Our modular frameworks was... Okay, so this part is wrong. So it's... Okay, so... Oh, what am I talking about? So this sentence definitely goes. We validate our pipeline comparisons to known experimental carry predictions or carry distances. We validate our pipeline with comparisons to known carry distances and club head velocities. Supplementary simulation data for a real OpenCAP. Okay. So this is obviously wrong and out of date. I think this sounds pretty good right now. Double pendulum models of the golf swing are well established in sports science literature, yet most studies focus on theoretical. What does that even mean, theoretical? Or expensive motion capture. Either theoretical dynamics or expensive motion capture. Double pendulum models of the golf swing are well established in sports science literature, yet most studies focus on either theoretical dynamics or expensive motion capture. We present an open source pipeline that 1. Uses OpenCap's video analysis to extract shoulder torque, 2. Forward simulates a subject-specific double pendulum model in the Julia programming language package modeling toolkit, and 3. Augments the swing model with a ball trajectory model to predict carry distance. We validate our pipeline with comparisons to known carry distances and club head velocities. This flexible, low-cost approach lowers the barrier for amateur golfers, coaches, and biomechanics researchers to explore model variants and ultimately optimize swing mechanics outside of specialized labs. That actually sounds pretty good. I don't hate that. Traditional estimation of golf swing kinematics from motion capture is prohibitively expensive for all but professionals due to the cost of motion capture systems and the time required for experts to manually track position markers. This work builds on top of advances made in computer vision for kinematics estimation to drive a player-specific double pendulum swing model and a ball trajectory model. This addresses the gap between hobbyist understanding and theoretical tools by giving players easily understood metrics on their swing, including airborne carry distance and club head speed. The Lagrangian double pendulum has been a canonical and central model in golf swing dynamics since 1970. The modeling toolkit package in the Julia programming language offers a way to construct and compose differential equation models. We provide an open source implementation of the Lagrangian double pendulum model and ball trajectory model in modeling toolkit that is flexible and modular, allowing for modifications and extensions. All the layouting is going to take so freaking long, bro. I still need some results, though, but I think it sounds a little better than it was. Okay, so let's just keep reading. Our work enables users, I don't know. Enables players to film their golf swing and use it to drive a carry distance prediction model. Block diag demonstrates a block diagram view of the components of our work. We begin by reviewing the classical mechanics of the forced double pendulum, which is the most widely used model for golf swing kinematics. We then introduce our ball trajectory. What is this thing? I saw it before. What is that thing? Oh, is that what you do? You add a little... Oh, that's so funny. I didn't even know that's what you're supposed to do. That's random. We then introduce our ball... Okay. Let's do... What if we did top and then top? Bro, it's starting to look so fucking cool. We begin our work by reviewing the classical mechanics of the forced double pendulum, which is the most widely used model for golf swing kinematics. We then introduce our ball trajectory model. The notation used in the equations will match figure in table 1. Or figure 2 in table 1. We use single and double pendulum equations to generate shoulder and wrist motions. The equations of motion are derived using the forced Euler-Lagrange equations. T is the kinetic energy of the system and V is the potential energy. Theta I are dependent variables of the system. Dot theta I are the angular velocities. Wait, but so we should say... Dot theta I are the angular velocities of the pendulum, also referenced also as omega I. And Qi is the forcing function on theta I. The initial conditions of our base swing model can be found in... The arm length and mass are from... Let me see how it reads. The initial conditions of our base swing model can be found in Jorgensen, 1970. The arm The arm length and mass are from Deleva 19. The shoulder torque, T-shoulder, can be found in Pickering and Vickers. The wrist torque is from Springs and Neal. Club mass and length are taken to be a driver and are readily found online. We begin with the unforced single point mass pendulum, which has the following Lagrangian and equations of motion. By solving these ODEs numerically, we can find omega... By solving these ODEs numerically, we can find... Bro, I don't know if I wrote that. That sounds like some fucking... We can find omega? Bro, you know that some random person wrote this. This is stupid. So I need some single uh the thing about the single pendulum that's easy is that you can stop it. Actually, how else do you stop it if theta is equal to 0? Single pend. So the single pend is that you have both of your arms completely straight. The full written Lagrangian and differential equations are meant for reference but not interpretability. Review the code in Jane for the full derivation. The Lagrangian is this. The differential equations are long. See section A for the full equations of motion. We now discuss the methodology for determining the club head speed at the time of collision. We implement a callback in the differential equation integrator that will perform a root finding routine to calculate the exact time when theta 1 is equal to theta 2. This condition corresponds to the point where the club and arms are aligned. A limitation of this approach is that for most initial conditions and forcing torques, there is no guarantee that the collision condition will be satisfied at the point where the ball is. Guaranteeing that the stopping condition occurs in Cartesian coordinates would require solving for the torques that would produce this condition. This is known as a shooting problem for boundary value problems and could be addressed in the future. I think that's fine. I don't hate that, you know. Okay, that's fine. Momentum transfer. The transfer of momentum from the club to the ball in our model is governed by elastic collision. The velocity of the ball can be calculated by solving the system of equations that relates the conservation of momentum and conservation of kinetic energy. If m1 and v1 are the mass and velocity of the club head, and respectively, and m2 and v2 are the mass and velocity of the ball, we can then we can then obtain the following system of equations. We assume the ball has zero velocity before impact, and v1 prime and v2 prime are the velocities after collision. The solution set will include a trivial solution Bro, I love that you can click it. That's so sick. The other solution provides us the true final velocities. We then use a club-specific loft angle and the magnitude of v2 prime as the initial condition of the trajectory model. The assumption of elastic collision is discussed in section 5. Okay, so wait, where are all my... Because I just keep kicking the can down the road, you know what I mean? It's discussed later, bro. I promise. Everything is in there, you know? A ball trajectory model was created to predict the airborne distance of the ball, given given the initial velocity magnitude as a result of an elastic collision. The specific club used determines the horizontal and vertical components of this vector. two model variants were compared, one in which the only force acting on the ball is gravity, and another in which drag slows the acceleration of the ball proportional to the velocity. In section 4, we analyzed the validity of these two models. See, that's what I'm saying, bro. Every time I got an @ sign, I know that I got more work to do. The first model has only gravity affecting the ball that follows the following equations. I think what I want is, can I put equations in a figure? I'm curious. All right, let's just undo this. How do you reference equations? I need to look that up. Why you got two tabs open? All right. Um. Okay. Usually papers don't really do this, but I don't honestly don't read enough papers. For our data collection, we use the applications OpenCap and OpenSim to analyze the mechanics of the golf swing by combining motion capture. OpenCap uses two cameras recording simultaneously to estimate 3D joint positions and segment motions during the swing. Beautiful sentence. Clear, good. I like it. The process begins with camera calibration using a checkered board, which helps determine the camera's parameters by defining their position and orientation relative to each other. The subject is then analyzed in a resting position with height and weight specified to scale the subject's musculoskeletal model. Beautiful. After calibration, we recorded the subject's after calibration, we recorded After calibration, a subject was recorded performing a golf swing. This was done multiple times both with and without a golf club and from various angles to ensure the best possible results. The captured swing is then processed So I'm just gonna say we used the application's open cap to analyze the mechanics of the golf swing to capture and open cap and open sim. We use the application's OpenCap and OpenSim to capture and analyze the mechanics of the golf swing. OpenCap uses two cameras. OpenCap uses two cameras recording simultaneously to estimate 3D joint positions and segment motions during the swing. The process begins with camera calibration using a checkered board. After calibration, a subject was recorded performing a golf swing. This was done multiple times, both with and without a golf club, from various angles to ensure the best possible results. The captured swing is then processed to generate detailed biomechanical data, including The captured swing is then processed to generate detailed biomechanical data, including body movement and joint angles. This motion data is imported into OpenSim, an open source software that replays motion data and can simulate the musculoskeletal system. OpenSim in future, the usage of OpenSim for more extensive analysis of how muscles, joints, and forces contribute to the golf swing by performing inverse kinematics is the usage of OpenSim for more extensive analysis of how muscles, joints, and forces contribute to the golf swing by performing inverse kinematics is discussed in future. Okay, great. So let me read this paragraph one more time, vet it for my own personal, We use the applications OpenCap and OpenSim to capture and analyze the mechanics of the golf swing. OpenCap uses two cameras recording simultaneously to estimate 3D joint positions and segment motions during the swing. The process begins with camera calibration using a checkered board, which helps determine the camera's parameters by defining their position and orientation relative to each other. The subject is then analyzed in a resting position with height and weight specified to scale the subject's musculoskeletal model. After calibration, a subject was recorded performing. After calibration, let's say the subject. So, a subject. Thus, after calibration, the subject was recorded performing a golf swing. This was done multiple times, both with and out a golf club, and from various angles to ensure the best possible results. The captured swing is then processed to generate detailed biomechanical data, including body movement and joint angles. Yeah, I mean, it's kind of redundant, but it's fine. This motion data is imported into OpenSim, an open source software that replays motion data and can simulate the musculoskeletal system. So we need to cite OpenSim. OpenSim. There's got to be a paper, right? The original paper. How to acknowledge us. There we go. Plus, 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 plus. Plus, 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 plus. So, yeah. That's okay. So this is just going to be OpenSim. Actually, do we already have this? It's likely that I'm just duplicating all my bibliographies. No, I thought not. Bro, why do they always do this with that freaking abstract in it? I don't know. Oh, wait, no, is this going to be disgusting? Oh, good. Wait, but in the bibliography, that's the question. Bro, Ploss? Dude, Ploss bothers the fuck out of me. I swear to God. He's got a fucking 1,000 middle names. He's got 1,000 middle names, everyone. It's got a damn 1,000 middle names. Great. And I got rid of the freaking dumbass thing. Oh, yeah. Wait, main.bib. Okay. Pickering and Vickers. Because in the methodology, we need to discuss this. Jenkins, where does this come from? Wait, go back. I wish there was a back button. There's not a back button for navigation, but I wish there was. I could see how when papers get way bigger, it's like unmanageable. Where is this? Jenkins. Oh, that's me. I did that. I wish there was an easier way to like. Well, it's got a link, so. Dude, that's so cool, bro. Types is actually so good, dude. It's kind of crazy how good Types is. All right. Um. Great. All right. So, um, in the following plots, the downswing begins at approximately t equal to 3.5 seconds and lasts for a few hundred millis. In the following plots, the downswing begins at approximately t. This one's good. Okay, let me read this. This graph shows the right and left arm rotation. Arm rotation is the circular movement of the arm at the shoulder joint involving both. Unfortunately, though, all right. Wait, actually, can we hop on a call and then let me just mute my. All right, good. This graph shows the right and left arm rotation. Okay, this graph shows. Oh wait, I actually want to say up here. I forgot. Um. All right. All right. I'll be back. I had a salad and some cake, but that's not really a meal, actually. That's not really a meal. I don't like food. I love it. Okay, I'm back. And I'm gonna lie down for 5 minutes because I'm freaking tired, bro. Look at that body. Yes. Alright, wait, where are we at though? We're at this. So there's that data. I don't know what other plots we need. Alright. So okay, we never actually do inverse dynamics. It's future work. Alright, explain control. Yeah, so this is where I'm at right now. This is what I have to do. We have to figure out, what did we do? I don't even remember. Oh. Right and left pronation and supination. Yeah, good. A few important plots. Yes, so now the primary time series from the extracted motion capture used to extract shoulder. I gotta lie down. Give me a second, bro. I am fucking crashing. Ugh. Oy, oy, oy. All right. Fuck it. Fuck it. It doesn't get done if you're not working. Let's get fucking started. All right. Let's hop on, bro. All right. So, God, dude, I'm so tired. All right. So I need to go through fatigue surface. All this stuff is okay. I don't understand what the duplicate of this is. What is this section, dude? I don't even understand what this is. Wait, oh, we already had results. Where's 10? No, rest release. That's actually true. Muscle fatigue. Bro, someone loves muscle fatigue. I don't know who that is, but we need to unify. At okay, yeah, golfer data. So I need to redo the golfer data thing, but in results, or let's do this, and then we say we start the analysis. Okay, so let me just get an outline. So first we simulate. So actually, I guess I want not club data. Wait, this is bro. It compiled, dude. Why would you do that to me? Okay, so this data first okay, but it's gonna be the same regardless. We simulate, we detail the model parameters for three tiers of player: amateur, intermediate, and professional. These parameters are used. Experimental results are recorded in golfer data. Experimental results from external sources are recorded and used to validate or are used to compare to model results. Specifically, we take ARM in the first phase of validation. We simply take the shoulder torque, shoulder and wrist torque, as well as arm length, and forward simulate the swing model. We then compare the predicted club head velocity to ground truth. In the second phase of validation checks, we then compute the elastic collision. We then use the elastic collision estimates for V ball and compare. Is for checking the predictions of the trajectory model. First, we take the known V ball the thing that we need to know is the loft. First, we take the known V ball and forward simulate the trajectory and simulate and simulate the trajectory using standard driver loft angles found in table club data. The loft is a 10. The loft is a 10. I don't know what any of these calculations are. That's the thing. Is I just don't know what those calculations are. All right, so we're gonna have to we're gonna have to go to all of these freaking sources. Which of these was used the most? I don't know. We're gonna do it after. So, bro, am I allowed to take my pants off? All right. Let's go back to where we was. Um. Experimental swing results from external sources are compiled in golfer data. Compiled and golfer data for 3 tiers of golfer. Skill. The first phase of validation, we take the shoulder and wrist torque as well as the arm length and forward simulate the swing model. We then compare the predicted club head velocity to ground truth. The elastic collision estimates the second phase of validation is checking the predictions of the trajectory model. First, we take the known V-ball and simulate the trajectory using standard driver loft angles. Okay, so these are the 3 things that need to be done. Um, okay. Jesus, 9:25. Okay. Um, okay, so let's do this. What is that character? Actually, let's just leave it like this. Wait. I'm gonna end the stream, guys. But that's just because I gotta get on.